Half-bridge MOSFET driver is one of the most common MOSFET configurations. It's used in motor controllers and buck regulators and other stuff. The basic principle is that one of the two MOSFETs is turned on and the other one's off. When the low MOSFET is on, the load is shorted to ground. And when the high MOSFET is on, the load is shorted to the supply rail. Now note that in this system, if both MOSFETs are turned on, a short circuit happens. And that is called shoot-through current. And sometimes it can happen if you switch both MOSFETs at the same time. That is, the low is trying to turn off and the high is trying to turn on. Very momentarily, you'll have a moment where this one's only partially on and this is only partially on, and a little bit of current escapes through, and that will heat up your MOSFETs and not allow you to drive as big of a load. And so the solution is called dead time insertion, and all that means is waiting for one MOSFET to fully shut off, waiting a known period of time determined by how long it takes the MOSFET to turn on and off, and then actually trying to turn the other MOSFET on and off. For this demonstration, I have a MOSFET circuit set up, a half bridge, with the LM5109 high and low gate driver and two IRLR 8726 MOSFETs. And I'll be using an Arduino to provide the high and low PWM input signals, and as well as performing dead time insertion. With the scope hooked up to the Arduino outputs, let's take a look at this. So see how the top MOSFET and the bottom MOSFET are never on at the same time. Initially, the top MOSFET is on, and then momentarily before the bottom MOSFET wants to turn on, the top MOSFET turns off and waits a small period of time before the bottom MOSFET will go ahead and turn on. So let's zoom in on this, and you can see when we talk about dead time, that's in between the blue line dropping and the yellow line rising up, and that is what the Arduino program needs to do if it's to avoid the shoot-through current situation. If you have a little bit of time, I would recommend trying to build the circuit yourself if you want to learn about MOSFETs. Now, you don't need the gate driver, and this might be easier to build if you used a P-channel MOSFET and an N-channel MOSFET, though the gate driver allows very snappy and quick rise and fall times that might be helpful whenever you're playing around with dead time. And actually, now that I think about it, without a gate driver, just using an Arduino pin to directly control the MOSFET gates, the rise and fall time will be slower, and that would make the effect of not having dead time even worse, since it would be easier to have both MOSFETs caught in the in-between stage as they are rising and falling. So that said, I'm going to show you an approach that you can take in an Arduino to get that working in the software. This will be a high-level overview of the approach that I'm taking, and that's because I'm using my own library for the Atmega 328 for interfacing with the timers rather than using the direct register addressing, which can be very difficult to read. So, for example, when this first line sets the timer to prescaler to 8, waveform generation mode 0 is normal timer operation, and that means that it's counting up, and it will generate a overflow interrupt if we enable that. And we also want to enable the interrupt for the compare match A unit. And so we'll set the high pin high, the high MOSFET. We'll turn on the high MOSFET and turn off the low MOSFET. So basically we want to energize the load at the beginning of the timer cycle, or really after an overflow, which is after the overflow it starts back at 0. So at the beginning of the timer period, you turn the load on. What you do is you turn the low MOSFET off, and then you wait either dead time to make sure that it's fully off, and then go ahead and switch the load on. And then the timer continues to count up and up and up until it reaches the value of the compare register, which is 200. So after 200 cycles, then we want to turn the load off, wait the dead time, and then turn the low pin on, and that'll drive the output to ground. And then that repeats. So that's the code that's running on the Arduino, and an approach that I think is viable. You could do it without using interrupts, but you'll be able to get faster frequencies if you do it this way. So yeah, play around with this. You'll probably have to use the data sheet to help you figure out what registers in order to use the timers. It's a little bit of an advanced thing with Arduino if you haven't done that before, but that's definitely the best way to do this dead time insertion. Give you greater control of the timing. Lastly, I just want to comment that you can't use delay function inside of a interrupt service routine. So instead, just use a for loop using a known number of cycles, clock cycles, which in my case it came out to be like 4 clock cycles. And you could probably use the same number if you're using an Arduino. That equals about 300 nanoseconds, which is a pretty generous. That should work for a lot of MOSFETs if you're using a gate driver. And then just make sure that you have the instruction, the assembly instruction, no op, so that the compiler doesn't think that you're doing a useless for loop and remove it and not actually compile it. So that's it for the Arduino code. And once you have proper dead time insertion, you can go ahead and turn this on and drive a small load. So I hope you found this video useful in explaining half-bridge drivers, and please take the time if you're interested in learning to build your own half-bridge circuit. And just because it's a very common electronic circuit, and you'll definitely put it to use if you have any interest in making motor controllers and other cool gadgets like that. So thank you for watching.